important is we're going to have a train.csv file, we're going to have a test.csv file, and we're going to have labels and images. So inside this, there's going to be, I don't want to open it because it's going to take a long time. Whatever, let's open it. All right, so there we go. We get a ton of images. All right, I think it's, I don't know how many, 25,000 maybe, 30,000. So we get all of those. And if we go back, if this will load, I already regret doing this. So then we have the labels, and I'm not going to open that, but those are just text files. Okay, I'm going to open it. So there we go, just text files. And if we open up this, for example, what we'll see is this right here. So we'll see, first of all, which class this belongs to. Then we'll see the center location, and then we'll see the, wow, this is so annoying. So the first thing we're going to see is the class probability. Then we'll see the midpoint. Then we'll see the Y midpoint. Then we'll see the width and the height. Now, one thing here is that these are not relative to a cell, right? We can't know. That depends on how we've split it. These are relative to the entire image. And so what's great is that if you resize it, to different number of pixels, then this is still going to work since it's relative to the entire image. So one thing that I think a lot of you are starting to realize is that, well, we're going to have to do this conversion of having from the entire image to having just the ratios for each cell. So that's one thing we're going to do in our dataset class. But anyways, that's how the data is structured. So in this case, this image would have two bounding boxes, two different objects of class 11 and class 14. All right, so that was kind of for making it easy. If you just want to download from Kaggle and you'll be done, so to speak, you don't have to do anything. If you want to do it by not downloading from Kaggle, or you want to see what it does step by step, then you can read this bash script. But what it's going to do is if we run that, so let's see, yeah, if we run that, then it's going to, first of all, download those data sets. It's going to it's going to sort of unzip them or untar them, I guess is the correct. But it's going to do that, and it's going to do a lot of pre-processing, and it's going to generate the CSV file and all of that stuff. But I don't want to focus too much on that. If you really want to read more about it, then you can read through this generate CSV file and go through the bash script of what's actually going on. But I'm assuming that for the majority of you, that's not interesting. And so just download this zip file from Kaggle and unzip it, and you'll have everything you need. All right, so now we gotta implement this stuff, right? All right, so now that we have the data in a data folder, we're gonna do vim dataset, open up the dataset Python file, and we're gonna import torch, we're gonna import os, import pandas as pd, and from pill import image. So those are the packages we're gonna need. And we're gonna first do class voc dataset, and we're gonna do torch utils.data.dataset. We're gonna inherit from that. Then we're gonna do define init, and we're gonna do self. We're gonna send in a CSV file for the locations of for the CSV file that contains the image and also the label. So let me actually be a little bit clear on the data. So, we took a look at the images and the labels, but one important thing is that we actually need to understand the CSV file. So if we open up, let's say this train.csv, then we'll have the image, in this case, 5.jpg, and then 000, same number of zeros, 5.txt. So we have the image and we have the text file. And so they're located in this folder right here for images and then in labels. But of course, everything is sort of in that CSV file. So we're going to have CSV file. We're going to need to know the image directory. We're going to need to know the label directory. Then we're going to need to know the split size, the number of bounding boxes, and then see the number of classes. Then if we have potential transformations we want to do, we're going to set that to default to none. And I'm not actually going to go through data augmentation for object detection in this video, But if that's something you would be interested in, let me know, and I'll consider making a separate video. All right, so then we're going to do annotations. We're going to first read that CSV file. So we're going to pd.read_csv of that CSV file. We're going to do self.image directory to be image directory, label directory equals label directory, and then self.transform equals transform, and then self.s equals s, self.b equals b, self.c equals c. All right, so then we're going to do the length. So that's going to be return the length of self.annotations. And if you're confused of any of this so far, then make sure you watch my video on creating custom dataset loading. So we're going to do then get item, self, and then comma index. So what we got to do first of all here is that we're going to find the label path. So we're going to do the label path is ospath.join of the self.label directory, which is just the directory we saw in labels, and then self.annotations dot we're going to locate an index row, and then we're going to take the first column because that's where the text file is. Then we're going to do boxes. It's just an empty list, and we're going to with open label path as f. So now we're opening that text file. We're going to do for label in f.readlines. We're going to do class label, comma x, y, width, and height. So this is going to be equal to float x. And I'm going to write this out and I'm going to explain it in a little bit more detail. If float x is not equal to int of float x, else integer of x. And we're going to do that for x in label.replace. We're going to replace a new line with just empty space, and then we're going to do dot split. So all right, so what am I doing here? Remember that the class is going to be an integer, and we want that to be an integer, but the rest of them, x, y, width, and height, are very likely going to be floats. So what we're doing is that we want to take the float if the float is not equal to the integer of that float. So remember, it's a string, so when we're doing float, we're converting it to a string, and then we're taking the integer part of that. So if they're not equal, then it means that it's a float, right? So we're going to take the float of x, converting that string into a value. Otherwise, we want to take the integer. If they are in fact equal, then that means that it's just an integer, and we want to do integer of x. All right, so then we have the class label x, y, width, and height. And what we're going to do is boxes.append. We're going to append class label x, y, width, height. So, sort of in summary, all we're doing is we're reading that a particular line, we're converting it to floats and integers, and then we're appending it. All right, so then we're kind of done with the label part, and we're now interested in the image. So we're going to image path is ospath.join, self.image directory, and then self.annotations.locate, index, and then 0. So that 0. So we're sort of getting the image directory, and then we're getting the image file name, which is index, comma 0. Then we're going to do image equals image dot open of image path. We're using pill here. Then we're going to do boxes is going to be torch.tensor of boxes. So we're just converting it into a tensor. And actually, I'm not sure if we need to do that. So we're converting it to a tensor, and then we're doing if self.transform. If we have transforms, we're going to do image.boxes equals self.transform of image, comma boxes. And I guess why we want to send in both here is because if you're doing, let's say you want to rotate the image, then this is getting into data augmentation for object detection, which can be quite tricky. But in many cases, let's say you're doing a random horizontal flip, then you obviously want to change the boxes as well. We're not going to go into that in this video though, but that's how you would do it. Then we're going to do the label matrix. It's going to be torch.zeros of self s, self c plus 5 times self comma b, right? So it's just going to be S, S, and then 30, or rather, no, sorry, this should not be self.b here. Yeah, so sorry about that. This should be just +5 because we should only have one bounding box per cell. But now I'm kind of afraid that this is going to break something, but let's see. So then we're going to do for box in boxes. And what we kind of want to do here is we need to convert everything to fit this label matrix right here. Remember that this is now relative to the entire image. And we want to first see, well, which cell does this bounding box belong to? And then we need to convert it to be relative to that cell. So we're going to do class label xy with height equals box and then dot to list. So this looks kind of weird in a way. Why are we converting it to a tensor and then converting it back to a list? But I think the idea is here that if we're doing any transformations, you most likely are going to do them in PyTorch. So that's why we're doing it that way. And then here we gotta convert them back. But yeah, so there you could probably also change them in this. But anyways, we're converting it back to a list now. And let's just make sure that the class label is in fact an integer. So let's do integer of class label. All right, so now we want to convert to seeing which cell row and cell column should this belong to. And how we do that is we do I comma j to be the integer of self time comma s times y. That is the row that it's going to belong to. And then we do integer of self.s times x. And that's going to be the cell column. So, remember, this is going to be a ratio between 0 and 1, and we now want to convert it where every cell is 0 and 1. So to know which cell row and cell column it should belong to, we just need to scale it appropriately by multiplying with the number of cells that we have. And then we take it, sort of down by taking the integer of that. And then we do that. The x relative to the cell and the y relative to the cell is going to be self.s times x minus j, and then self.s times y minus I. So then we're kind of doing this relative to the cell by removing in which part of the cell it's in. So yeah, maybe these two lines can be a little bit tricky, but I recommend that you take an example, draw it out, and then do this by hand and see that it works, if it's not clear instantly, so to speak. And then to get the width compared to the cell and the height compared to the cell, all we have to do is take the width times self.s and the height times self.s. So remember, this is going to be the width and the height relative to the entire image. And if we want it relative to one cell, all we have to do is scale it appropriately with the number of cells we split it by. So that's how we get the sort of all of these are getting the locations relative to the cell. All right, so what we got to do now is we got to do if label matrix of the cell ij is equal to, and then 20 is equal to 0. So we're checking if there's currently no object in ij, which we just calculated that this object, this bounding box should be in. Then first of all, we want to make sure that this is now taken. So this is going to be 1 in the future. And then we're going to do that the box coordinates are going to be towards the tensor of x cell, y cell, width of the cell, and then the height of the cell. And we're going to specify that the label matrix I comma j and then 21 to 25 is equal to these box coordinates. And also that the label matrix of I comma j comma class label is going to be equal to 1. And so here we're just specifying which should contain the class, or which class it is for this object. And that's it. So what we got to do now, we just got to return the image and the label matrix. And I guess one thing to remember, recognize here, is that this is just for one example, but that's all we have to do with loading custom data in PyTorch. We specify how to load one example, and then we're going to have some efficient data pipeline that's going to batch and everything and do everything of that stuff for us. All right, so that's for loading the data. I know it's a lot. This is a large project, and I'm just going to check that this is actually correct. So I'm going to run this on the complete code, see that it works. So we're going to do Python train.py and Python. So I've now copied in replacing the other data set, and that's not correct. So let's see, on line 24, right there, got to do label path. So let's bring that back. Okay, so after some troubleshooting, I found that another file that I am using is assuming that the shape of this should be 30 for the labels and predictions. So we're gonna have to self.b, so it's 5 times self.b, and that makes so that I don't have to modify the other file. But just note here that the additional 5 nodes is not going to be used. The only things that's going to be used are the 25 first nodes. So we're not going to actually need 30. That's for the predictions, because we have one additional bounding box. And so where I actually assume that this was 30 nodes is when later on reconverting this to being relative to the entire image. That's when and another function sort of was, I guess, assuming that this should be 30. But anyways, we can just put it to 30. It doesn't really matter. But that's just one thing to keep in mind. So, wow, we've now done, let's see, we've done the model, we've done the loss function, we've done the data set, and we're not gonna go through the utils, but what's going to be inside there is intersection of a union, null-max suppression, mean average precision, where we've done all of those 3 in previous videos. One additional function I'm gonna put in there is converting from relative to cell to being relative to the entire image. And I'm not going to show how to do that, but it's going to be on GitHub if you want to read it. I don't think that code is super interesting. And then what more? There's going to be one additional there as well, which is how we can plot these bounding boxes. And to save some time, I'm not going to go through that either. But that's also going to be in GitHub if you want to see. That's mostly for making sure that our model works. That's the only reason, basically. So what we're now going to do is the train function. So we're going to specify how the training should be done and all of that stuff. So let's open up vim train.py. And so we're going to import torch, import torch vision.transforms as transforms, import torch.optim as optim. Import torch vision.transforms.functional as functional transforms, FT. We're going to import, and so these are for the transforms, the optimizer. This is also for some image transforms we're going to use. Then from TQDM, import TQDM. That's a video I did on how to get a progress bar in PyTorch, just so that it looks nice. So that's all we're going to use that for. Then from torch.utils.data, import data loader. We're going to do from model, import YOLOv1. From dataset, we're going to import VOC dataset. From utils, we're going to import intersection over union, non-max suppression, mean average precision, and all of those 3 are separate previous videos in this playlist. So if you're unsure about any of these 3, check out those videos, because that's code copy pasted from those. Some more that we're going to need, and I'm not going to show how to implement these, but it's going to be on GitHub, but it's going to be cell boxes to boxes. So converting from the cell relative to the cell, so we get them in relative to the entire image. Then we're also going to do get bounding boxes, and this function is going to use this one, converting it, and then also get all of the bounding boxes. Then we're going to do plot image, and save checkpoint, load checkpoint. So I guess the only thing I'm not gonna show, these two I've done previous videos on, and hopefully this should be pretty simple. But this right here, sell boxes to boxes, get boxes. So these three, I'm not gonna show how to do. I don't think they're very interesting, but they're gonna be on GitHub. Lastly, we got to do from loss import YOLO loss. We're going to first set a seed. Let's say 1, 2, 3. Torch.manual seed of seed. And this is mainly so that we get the same data set loading, but that's pretty much all. And then let's set hyperparameters and so on. Let's first start with the learning rate. So learning rate, let's set it to 2e minus 5. Device, we're going to set to CUDA if torch.cuda is available. Otherwise, we're going to set it to the CPU. The batch size, we're going to set to 16. Because we have so large images and the model takes a lot, even if we've set the number of nodes to 496 instead of 4096, I can't have the batch size that they mentioned in the paper, which is 64. The maximum I can go is a batch size of 16, and so that might be saying that I need an upgrade in my GPU, but I'm using a GTX 1060, so I don't really have that much compute. But batch size equals 16 it works fine. So we're going to set weight decay equals 0. And so why we set the dropout to 0 and the weight decay to 0, why we're setting it here, is because I'm not actually going to train the entire model to re-implement the exact same results they got in the paper. And there are two reasons. First of all, that's going to take a long time to train. They pre-trained on ImageNet for 2 weeks, and then they trained on this data set for a long time. And they also did it with very heavy data augmentation. And frankly, even if they did it a couple of years ago, their GPU was a lot better than the one I have. So it's mainly because of computational reasons, and so what we're gonna do to make sure that this actually works is we're gonna first try to overfit a single batch. We're gonna plot and see that it makes sense, and also see that we get a mean average precision of close to 1. And then additionally, we're gonna overfit 100 examples. So those two are sort of sanity checks to make sure that our implementation is accurate. But to do that, to overfit more easily or faster, we're going to set so that we have no regularization. All right, so we're going to set epochs to, I don't know, 1,000, 100 maybe. And then we're going to set non-workers to 2. And this is a hyperparameter, so you play around with that. We're going to set pin memory to true. Load model to false. Then we're going to set load model file to be, we're going to call it overfit.pth.tar. So this is just so that we save the model that we overfitted, and we're going to run it later on to see that when we plot images and so on. So the image directory, first of all, then is going to be data images. The label directory is going to be data labels. All right. So, one thing we got to do is we got to make sure that they are resized. So I'm actually going to create, so we can use transform.compose, but that's not also going to take in the bounding boxes. And now when I think about it, when we're just doing resize, this is going to look a little bit odd perhaps. And you could just have done transforms.resize. And then when sending it in, you could just have only sent in the image because we're not doing any data augmentation on the label side. But in my implementation, I checked for doing some data augmentation like horizontal flip and random crops and so on. And this what I'm doing here is going to extend more easily if you have more data augmentation. So we're going to do our own compose. And we're going to do our init self comma transforms. We're going to do self.transforms equals transforms. Then we're going to, when we call this, we're going to send in the image and bounding boxes. we're going to go to for t in self.transforms. We're going to do image bounding boxes equals transform of image and then bounding boxes. And the reason here is because our transform that we're going to send in is only going to operate on the image. But of course, if you would modify them, then you would have that you would also do them on, you would then send in, if you would create your own, you would do like this. But so in this case, we're only going to do it on the image because we're only going to resize it. So do transform equals compose of transforms.resize, and we're going to resize it to 448. Then we're going to do transforms.toTensor, and we're going to close that list, and that's the compose. So we're going to resize and then transforms to tensor. One thing that could improve this is that you do a normalization, so you make sure you have mean 0 and standard deviation 1. But to tensor, I guess works fine in this case. All right, so then we're gonna define a training function. We're gonna send in a training loader, the model, optimizer, and the loss function. So what's gonna be done here is one training loop through the entire data set. First of all, we're gonna do loop is tqdm of train loader. We're gonna do leave equals true. This is from the video I did on setting up a progress bar. But then we're going to have mean loss is an empty list. We're going to go through for batch index, comma, x, comma, y in enumerate of this loop. We're going to do xy equals x dot to device, and then y dot to device. The out is going to be the model of x, and we're going to do loss is loss function of out and then y. We're going to do mean loss dot append loss dot item. So, obviously here we haven't actually created these things. We haven't created the loss function and so on. But this is going to be done later on. So we're going to do optimizer dot zero grad. We're going to do loss dot backward. Optimizer dot step. And then let's see, right here we gotta update the progress bar. So how we do that is we do loop.set postfix, and I'm just going to send in the loss. I'm just going to do loss equals loss.item. So for the progress bar, we're going to see that the loss updates for every batch. That's just a nice thing to have. And then we're going to print the mean loss was, and then sum of mean loss divided by the length of mean loss. So we get the mean right there. So that function is just going through the entire training loader one. So we trained on an entire data set. Let's put this centered. So what we got to do now is we're in main, and we got to initialize our model. That's going to be YOLOv1. We got to send in the split size 7, num box is 2, num class is 20, and then dot to device. We got to specify the optimizer. It's going to be optim.atom. We're going to send the model parameters. Learning rate is going to be the learning rate. Weight decay is just going to be equal to weight decay. And that's it for the optimizer. The loss function is going to be YOLO loss. And here we're going to do, so if load model, let's make sure that I did that. So load model is false in the beginning. So if we load a model, then we want to do load checkpoint, torch.load of load model file, model, and then optimizer also. So that's just if we have a model saved. And then we want to create a data set for training. So we're going to train data set is VOC data set of data. And we're going to specify the CSV file here. So that would be train.csv if you want to train on the entire data set. I'm not going to do that. I'm just going to do 8 examples.csv. So that's, I guess, a small batch of 8 examples. We're going to try to overfit on that first, make sure that works. And then I have another